Hello there, this is Dave Soraka, Madison College, Calculus and Analytic Geometry 1, Spring 2017, and this is the video lecture that I asked you all to view in place of our regularly scheduled class meeting for Friday, March the 31st, when I will be out of the office having my foot surgery. And I would ask that you please watch this video in its entirety before we reconvene on Monday. And I'll plan to keep this video at around the 50-minute point. I'm going to talk about section 4.4. I may or may not finish the entire section, so we'll see how it goes. I'll stop in the middle if I see that I've gotten to about 50 minutes. So as you can see, section 4.4 is titled Concavity and Curve Sketching. And as you can also see in the first sentence of my notes, in this section we're going to analyze the relationship between a function's second derivative and the graph. So what does a function's second derivative tell us about the graph of the function? We've learned quite a bit in the last section, section 4.3, and prior to that, what a function's first derivative tells us about the graph of a function. So namely, well, just to recap, at any value of x where the function's first derivative is equal to 0, the graph of the function has a horizontal tangent line. And that point where the tangent line is horizontal could correspond to a local maximum, could correspond to a local minimum, or it might just correspond to a plateau, a point that's neither a max nor a min, but where the function's graph just happens to momentarily level off. So we use a function's first derivative to find those critical points where the peaks and the valleys of the graph are. And as we found out in section 4.3 some additional information about a function's first derivative, wherever f prime of x is greater than 0, that implies that the function f is increasing. Sorry, I'll write as best I can. I'm using a stylus to write directly on a computer screen, and it's not the easiest thing to do. And likewise, wherever f prime of x is less than 0, then the function f is decreasing. So we talked about that in section 4.3. So wherever the first derivative is positive, that means that as we move from left to right along the graph rises. And wherever f prime of x is negative, the graph falls. Okay, so now let's move on and consider the function's second derivative. And to do that, what we want to do is think about this relationship here that I just reviewed between the function f and its first derivative, f prime of x. So a function is increasing wherever its derivative is positive, and a function is decreasing wherever its derivative is negative. Well, that relationship can also be applied to the relationship between f prime and f double prime. Because after all, a function's second derivative, f double prime of x, is really just the derivative of the first derivative. Therefore, if a function is increasing wherever its derivative is positive and decreasing wherever its derivative is negative, then it has to be the case that f prime is increasing wherever its derivative, f double prime, is positive. And likewise, f prime must be decreasing wherever its derivative, f double prime, is negative. Now we want to think about the implications of those two statements. What does it mean to say, or what is implied about the graph of the original function f if we happen to know that f prime is increasing? So that means that as we move rightward along the graph, f prime gets bigger. Now what does f prime measure? F prime measures the slope of the tangent line on the graph of the original function. So to say that f prime is increasing is equivalent to saying that the slope of the tangent line increases as we move from left to right along the graph. Now, what does it mean to increase a line's slope? Well, suppose the line initially has a positive slope like that. So that line that I just sketched on the screen, looks like it maybe has a slope of 1, perhaps a little bit less. What do I have to do to increase its slope? Well, I'd have to make it steeper. Maybe something like that. So that might be a line with a slope of 2 or perhaps 3. So in other words, if a line has positive slope initially, then to increase its slope, I would have to make that line steeper. Now, what if initially the line has negative slope? What do you have to do to that line to increase the slope? Well, you actually wouldn't make it steeper. You would actually make it flatter, more horizontal. This line perhaps looks like it has a slope of about -1, and this line looks like it maybe has a slope of about -1/2. Well, -1/2, remember, is actually considered to be a larger number than -1. Okay, so for any two numbers, the larger number is the number that lies further to the right on a number line. So -1/2 lies to the right of -1. And so -1/2 is considered to be bigger than -1. So again, we see that increasing the slope of the tangent line means rotating the tangent line counterclockwise. So for a line that initially has positive slope, you make it steeper. It just so happens that if a line initially has positive slope, you make it steeper by rotating counterclockwise. And if a line initially has negative slope, you make it steeper by making it, you rotate it counterclockwise to increase its slope. So in either case, increasing the slope of the tangent line implies rotating that line counterclockwise. So if you look at this very leftmost statement and this very rightmost statement, that's basically the punchline. If the second derivative of a function is positive, that means that as you move from left to right along the graph, the tangent line rotates counterclockwise. And likewise, if f double prime of x is negative, that means that f prime is decreasing, which implies that as we move from left to right along the graph, the slope of the tangent line decreases, which implies that if we move from left to right along the graph, the tangent line rotates clockwise. Okay? If you increase a line slope by rotating it counterclockwise, then you must decrease a line slope by rotating that line clockwise. So if we scroll down just a bit here, we see these two situations both illustrated. In this graph on the left, you see that as you travel from left to right, the tangent line would have to rotate counterclockwise. On this second curve, as you move from left to right, the tangent line is going to rotate clockwise. And so the figure on the left illustrates a situation in which f double prime of x is positive, and the figure on the right illustrates the case where f double prime of x is negative. More of a layman's way of thinking about this, so in non-mathematical language, the figure on the left looks like a smiling face, and the figure on the right looks like a frowning face. That might seem like kind of a silly description, but it is actually quite valid, and perhaps the easiest way to remember what's going on here. So, wherever f double prime of x is positive, we expect the curve to look like a smiling face, and wherever f double prime is negative, we expect it to look like a frowning face. And you see here and here, three different but equivalent ways of describing each of these two situations. So wherever the graph looks like a smiling face, you can describe that situation in slightly more mathematical terms by saying that the tangent lines lie below the graph near the point of tangency. And likewise, wherever f double prime is negative, tangent lines lie above the graph near the point of tangency. So the smiling face and the frowning face reminders are there. And then the third bullet points under each of those graphs, a curve in which f double prime is positive looks kind of like a bowl that would hold water, whereas a curve for which f double prime is negative looks more like a bowl that would spill water. Now we have official names for each of these situations. We say that the graph on the left is concave upward, and the graph on the right is concave downward. So f double prime of x greater than 0 is associated with concave upward, and f double prime of x less than 0, concave downward. And I think that's all we've got on the page. Okay, so let's skip ahead to the next page. So there's your official definitions of what it means to say that a function is concave up, or what it means to say that it's concave down. The function f is said to be concave up on an interval I if f prime is increasing on I, and the function f is said to be concave down if f prime is decreasing on I. Now that's not quite what I said on the previous page. What I said on the previous page is that f is concave up if f double prime is positive, and concave down if f double prime is negative. But that's equivalent to saying that f prime is increasing or f prime is decreasing, right? If f prime is increasing, then f double prime must be positive, because a function, in this case f prime, is increasing wherever its derivative, f double prime, is positive. So that definition is a little confusing because it describes concave up and concave down in terms of the first derivative. What I think you really want to do in practice is associate the phrases concave up and concave down with the sign of the second derivative. So there's what you really need to remember, is what's stated in that theorem. Wherever f double prime of x is positive, the function f is concave up, and wherever f double prime is negative, the function is concave down. Now, it is worth mentioning that the sign of the first derivative and the sign of the second derivative act independent of one another. So at any given point on a what I mean by that is that at any given point on a graph, the first derivative and the second derivative could both be positive. They could both be negative, but it is also possible for one of those quantities to be positive and one of them to be negative. And I'll just draw a rough sketch to illustrate each of those situations. Just off here on the side a little bit. Here is a curve in which f prime and f double prime are both positive. Remember that if f prime is positive, the function is increasing, meaning it rises as it moves to the right. If f double prime is positive, the function is concave up, which basically means that the graph looks like a smiling face. So what I just drew here is a curve that both rises as it moves to the right and looks like a smiling face. But you could also have a curve that rises as it moves to the right but looks like a frowning face. And so that's what I just drew here. That would be a situation in which f prime is positive because the graph is rising, but f double prime is negative because the curve looks like a frowning face. Likewise, this curve here is indicative of f prime being negative, but f double prime being positive. F prime negative because the curve is falling as it moves to the right, but f double prime positive because the curve looks like a smiling face. And then finally, this curve has the property that both f prime and f double prime are negative because the curve is falling as it moves to the right, and it looks like a frowning face. Okay, so let's look at a quick example here. Determine the intervals for which the function f of x equals 3x to the fifth minus 20x to the fourth plus 40x to the third is concave up, and the intervals for which it is concave down. So we answer this question by computing the second derivative of the function and determining where the second derivative is positive and where it is negative. So let's go ahead and compute two derivatives. I'll write as neatly as I can. So the first derivative is 15x to the fourth minus 80x to the third plus 120 x to the second, and the second derivative is 60 x to the third minus 240 x to the second plus 240 x to the first. And we are greatly aided here by the fact that 60 is a common factor. So is x to the first. So if I factor out a 60 and an x, I'm left with x squared minus 4x plus 4. And the expression x squared minus 4x plus 4 further factors into x minus 2 times x minus 2. So now we simply need to determine where is this expression positive and where is it negative. So let's draw a number line here. Now clearly the expression is equal to 0 when x is 0 and when x is 2. So I'll mark both of those numbers on my number line. And I think it's pretty easy to see that if x is to the right of 2, okay, that number line is essentially an x-axis. If x is to the right of 2, then f double prime of x is positive. Now if x is between 0 and 2, f double prime of x is still positive as a consequence of the squaring operation that's attached to the factor x minus 2, right? A square can never be negative, so it doesn't matter if x is a little bit greater than 2 or a little bit less than 2. In either case, x minus 2 squared will be positive, and as long as x is greater than 0, then this factor remains positive. And of course, a positive times a positive is a positive. So apparently, f double prime is momentarily equal to 0 at x equals 2, but is positive on both sides of that point. So whatever, that's just the way it is. When we move to the left of 0, we see that f double prime is now negative. So, and that's a consequence of the fact that this factor is negative when x is negative, but this factor is still positive because of the squaring operation. Okay, so I think we've got our sign behavior sorted out. So from this number line, we can probably go ahead and conclude that the function f is concave up when x is greater than 0, so on the interval from 0 to infinity, and that f is concave down when x is less than 0, so on the interval from negative infinity to 0. Okay, so of course that wasn't a terribly difficult example because it was just a polynomial, but it gets the ideas across. Okay, so let's skip ahead and see what we've got here on the next page. Okay, an important piece of terminology here. Inflection point. An inflection point is a point on the graph of a function at which the graph's behavior changes from being concave up to concave down, or vice versa, concave down to concave up. Okay, and that's spelled out very precisely in this definition here, but it's basically what I just said. Now, inflection points, please understand, are not the same as critical points. Critical points are points on the graph like here and here and here, where the first derivative is equal to 0 or is undefined. And as we know, those points, those critical points, are points at which the graph of the function is very likely to change from increasing to decreasing or from decreasing to increasing. Now, it might not do either of those things. It might be a plateau, but at a critical point, that's where we expect that there might be a change from increasing to decreasing or from decreasing to increasing. Inflection points are different. Inflection points are not points where we necessarily change from increasing to decreasing or from decreasing to increasing, but rather points where we change from concave up to concave down or concave down to concave up. And those are a little bit harder to spot, but in the graph that we see here, the points P, right about there, and Q, right about there, those are our inflection points. Because as we can see, to the left of point P, the graph looks like a smiling face, more or less, and immediately to the right of P, the graph begins to look like a frowning face. And then likewise at point Q, the graph appears to transition back from being a frowning face to looking like a smiling face. So it can be a little bit imprecise to pick out exactly where the inflection points occur. It might be kind of helpful to remind yourself of an alternative way of thinking about concave up and concave down. Wherever a curve is concave up, the tangent line rotates counterclockwise as you move from left to right along the graph. And wherever the graph is concave down, the tangent line rotates clockwise as you move left to right along the graph. So if you just imagine traveling from left to right along this graph, point P is the point at which the tangent lines will stop rotating counterclockwise and begin to rotate clockwise. And then as you pass through point Q, that's the point at which the tangent lines change from rotating clockwise back to rotating counterclockwise. And I'm not quite sure why I traced over that graph, since all I really did was make a mess of it. But I hope you get the idea there. Okay, so the next thing we want to talk about here is something called the second derivative test. Now, this is similar in many ways to the first derivative test that we talked about in the previous section. Let me remind you what that was all about. Suppose we have calculated the first derivative of a certain function, and we have discovered that the first derivative of the function is equal to 0 at a particular number c. So c is a critical point. Now suppose we investigate a little more closely and we discover that f prime of x is negative when we're slightly to the left of c, but positive when x is slightly to the right of c. That means that the function is a decreasing function to the left of c and an increasing function to the right of c. So the graph falls as it travels rightward towards c, but then rises as it continues to the right past c. So we transition from a decreasing to an increasing function as we pass through c, and that implies that the function has a local minimum at c. Okay, so that's an illustration of what we referred to yesterday as the first derivative test. Find all of your critical numbers, set up a number line, and determine the sign of the first derivative on either side of each of your critical numbers. And if f prime is negative to the left of the critical number and positive to the right, you've got a local min. If f prime is positive to the left and negative to the right, you've got a local max. And if f prime has the same sign both to the left of and to the right of that critical number, then that a critical number corresponds to neither a local maximum nor a local minimum, but rather a plateau. So that was called the first derivative test for classifying the critical numbers. Well, it turns out there's another way to determine whether a critical number is a local maximum or a local minimum, and it's called the second derivative test. And the idea is pretty simple. If you've got a critical number, or let's say a critical point, and the graph happens to look like a smiling face as it passes through that critical point, well, that would seem to be suggestive of a local minimum. On the other hand, if you've got a critical point and the graph looks like a frowning face as it passes through that critical point, that would be indicative of a local maximum. And what is it that tells us whether a graph looks like a smiling face or a frowning face? Well, that would be the sign of the second derivative. So that hopefully makes sense out of the following theorem, which is known as the second derivative test. Suppose f is continuous on some interval ab, and suppose the number c is a critical number that lies in that interval somewhere, and suppose it's a critical number for which the first derivative is equal to 0. What we do is we compute the function's second derivative, and we plug that critical number directly into the second derivative. If the second derivative turns out to be negative at the critical number, then we've got ourselves a local max. And if the second derivative is positive at the critical number, we've got ourselves a local minimum. So this is a very quick and easy test to implement as long as you can easily compute the second derivative. You go ahead and compute it, and you plug in each of your critical numbers one by one. And if the second derivative spits out a negative output, you've got yourself a local max. If it spits out a positive output, you've got yourself a local min. Now you should be wondering, what if you plug that critical number into the second derivative and you get a 0? You're probably thinking that that likely implies, or that must imply, that we've got ourselves a plateau, a point that is neither a local maximum nor a local minimum. I wish that I could tell you you were correct, because that would actually make a lot of sense. Unfortunately, it's not quite that simple. It turns out that if f double prime of c is equal to 0, then that critical number c might correspond to a plateau, but it might also correspond to a local maximum or a local minimum. You really just don't know without further investigation. So as I say below the theorem, if the second derivative spits out a 0 when you plug in the critical number, the second derivative test, unfortunately, is inconclusive. So you cannot conclude that it's a plateau. It might be a plateau, but it might also be a local max or a local min. You need to try to answer that question by other means, like perhaps the first derivative test, which is capable of concluding when you have a plateau. Namely, if the first derivative is negative both to the left and to the right of the critical number, then you've got a plateau. Or if it's positive both to the left and to the right. So the second derivative test, even though it's easy and quick to use usually, is unfortunately inconclusive some of the times. So let's see if I got an example on the next page. Okay, we do have a nice example here. So it looks like this is a 6 or 7 part example, so it's going to take us a few minutes to go through it. So I'll work my way through this example, and then we'll bring this video lecture to an end, because I think I'll be at about the 45-minute mark, or about the 50-minute mark by then, maybe even a little bit beyond. Anyway, so this is a nice summary example that reviews a lot of the things that we've learned both in this section and in the previous section. So here we have a polynomial function, and we want to do lots of things and find lots of things out about that function. So let's compute its first 2 derivatives. So f prime of x is going to be 12x to the third minus 12x to the second minus 24x, and the second derivative is 36x squared minus 24x minus 24. Okay, that was simple enough. Part B, determine the critical numbers. Well, the critical numbers are the values of x in the domain for which the first derivative is either equal to 0 or undefined. And I think we will all agree that a polynomial function is never undefined, so we just need to figure out where that first derivative is equal to 0. And I think that'll be pretty easy to do as long as we can factor this without too much trouble. So I can factor out a 12x, leaving behind x squared minus x minus 2, which I can further factor into x minus 2 times x plus 1. And so the critical numbers are 0, 2, and negative 1. Okay, so that's something you should already have known how to do. Part C, determine the intervals on which f is increasing and the intervals on which f is decreasing. So to answer this, we draw a number line. We denote all of our critical numbers on that number line, arranged properly. So negative 1, 0, and 2. And what we do is we try to determine the sign of the first derivative in each of the 4 intervals that you see on that number line. And it's easier to work with the factored form of the first derivative to answer this question, so that's why I circled it. So if you look at that expression, it shouldn't be hard to convince yourself that f prime of x is positive if x is to the right of 2. When we cross to the other side of 2, that middle factor, x minus 2, turns negative on us, and so now the expression looks like a positive times a negative times a positive, and that results in a negative. So in this interval, f prime of x is less than 0. When we cross 0, now that first factor, 12x, turns negative on us, and so now the expression looks like a negative times a positive. That's going to result in a positive. So f prime of x is positive in this interval. And then finally, when we cross negative 1, that third factor goes negative on us. So in this leftmost region, all 3 of those factors are negative, resulting in a negative product. So f prime is negative in that leftmost interval. So f is increasing wherever its first derivative is positive. And so that would be on the intervals negative 1 to 0 and 2 to infinity. And likewise, the function would be decreasing on the interval from negative infinity to negative 1, as well as the interval from 0 to 2. Hope you can read my writing. Sorry that it's so messy. Okay, part D. Apply the first derivative test to classify each of the critical numbers that you found in part B as corresponding to a local maximum, a local minimum, or neither. Well, this is easy because we've already done all of the necessary work in part C. There's really no additional work we need to show here. We just need to draw conclusions based on the analysis that we've already performed in part C. If you look at that number line, you see that f prime of x is less than 0 to the left of negative 1, greater than 0 to the right of negative 1. And so as the graph passes through x equals negative 1, it transitions from a decreasing function to an increasing function. So, right, we have decreasing in this interval, increasing in this interval, decreasing, and increasing. So as the graph moves from left to right, if it transitions from a decreasing to an increasing function, we've got ourselves a local min. And if it transitions from an increasing to a decreasing function, we've got ourselves a local max. So obviously, based on that number line, we've got local mins at x equals negative 1 and x equals 2. And we've got a local max at x equals 0. Okay, part E. Confirm your conclusions, if possible, by applying the second derivative test. So I need to scroll back up here briefly to remind ourselves that the second derivative of this function is 36x squared minus 24x minus 24. So let's recopy that. So it was 36x squared minus 24x plus 24. F double prime of x, 36x squared minus 24x plus 24. For the second derivative test, all you do is you plug each of your critical numbers directly in to the second derivative. So I just need to compute f double prime of 1, f double prime of 0, and f double prime of 2. Now let's see if I can do this in my head. F double prime of negative 1 would be 36 plus 24 plus 24. Well, that's 12. And the fact that this is a positive number means that as the graph passes through x equals negative 1, it looks like a smiling face. Now we already know that negative 1 is a critical number. The graph has a horizontal tangent there because the first derivative is equal to 0 there. Now, by virtue of the fact that we got a positive number here, that tells us that not only do we have a horizontal tangent at negative 1, we have a graph that looks like a smiling face there. And so that must correspond to a local min, which agrees with our answer in part D. If we plug 0 into the second derivative, we get 0 minus 0 plus 24. That's obviously 24. Let's see, did I copy that down correctly? Oh no, I'm sorry. The second derivative is 36x squared minus 24x minus 24. Well, that changes things, doesn't it? I'm sorry. That's a negative, not a positive. My mistake. So let's see. does that change our conclusion here at -1? Let's see, 36 plus 24 minus 24. I guess this answer should have been 36, not 12. Okay, well, sorry about the mistake there, but still a positive number, so same conclusion. We've got a minimum at x equals -1. So f double prime of 0 is actually -24, not positive 24. So we've got a horizontal tangent at 0 because the first derivative is 0. We've got a frowning face at 0 because f double prime is negative, and so that implies that we've got a local max at x equals 0. Finally, f double prime of 2 would be 36 times 4 minus 24 times 2 minus 24. So let's see, that's going to be 144 minus 48 minus 24, and I believe that's 72. So f double prime of 2 is positive. That means we've got ourselves a local minimum at 2. Because the graph looks like a smiling face there. But we've got a critical point. Okay, part F. Where is F where is F concave upward and where is F concave downward? So the intervals on which F is concave upward and concave downward. To answer this question, we would like to be able to factor the second derivative completely. I'm going to see if I can do that. I see I can factor out a 12. So if I factor out a 12, that leaves behind 3x squared minus 2x minus 2. And unfortunately, this expression does not factor easily. It turns out that if you set that quadratic equal to 0, so if you set 3x squared minus 2x plus, or minus 2 equal to 0, you will discover that it is equal to 0 at 1 plus root 7 over 3 and 1 minus root 7 over 3. And you can also fairly easily show that when x is to the right of 1 plus root 7 over 3, then f double prime of x is positive. When x is between those two roots, f double prime of x is negative, and then when x is to the left of 1 minus root 7 over 3, f double prime of x is back to being positive. And so the function is concave upward. I'll just abbreviate since I can't write very well with this stylus and I'm running out of room. So it's concave upward to the right of 1 plus root 7 and to the left of 1 plus root 7 over 3 and to the left of 1 minus root 7 over 3, and it is concave down when x is between 1 minus root 7 over 3 and 1 plus root 7 over 3. And so that means that the function changes from being concave up to concave down at 1 minus root 7 over 3 and changes from being concave down to concave up at 1 plus root 7 over 3. And at any point on the graph where the function changes from concave up to concave down or from concave down to concave up, we call that point on the graph an inflection point. And so 1 plus root 7 over 3 and 1 minus root 7 over 3 are both inflection points of this graph. Okay, so I think that takes me to about the 50-minute mark or so, so I'm going to call it quits. And I thank you for listening. I hope this made sense, and we'll see you all on Monday.